Alright, we're going to talk about work and power. Make sure you guys know what's going on if you were absent. So remember, we talked about a shopping cart full of groceries sitting in a grocery store. Because it's sitting, we said it has no energy. As long as it's not up on a hill, it doesn't have any potential energy. And if we apply a force to the same cart of groceries, just because we apply a force does not mean we give it any more energy, because this doesn't specifically say that the cart is actually moving. So if the cart is not moving, we haven't applied any energy. And so that point about moving is very important as we move into talking about work. So work, in the notes that you have, remember that work is done when a force moves an object through a distance against another force. So the key here is this part about moving an object. Let me see if I can get this going. Let's see. Pen. Ooh, what happened? There we go. So moves an object is the key point here, through a distance against another force. Okay, this moving is the key thing. So I can push a book across a table, and when I do that, I am doing work because I'm moving an object and I'm doing it against friction. That's what's causing the movement. So let's move forward now. Our equation for work is this: work equals force times distance. So if we apply a force and an object moves a certain distance, then we have done some work. Notice that only parallel forces are going to go in here, into this equation. The reason for that is because if we apply a force that's perpendicular, for instance with the book, when I push the book across the table, there are also some other forces that are going on. That would be gravity and normal force. So I can draw that right here. This is the book, and if I could apply a force this way, it causes the book to move. But we also have gravity going on. That's a force. We also have normal force going on. So this would be normal force here. This would be gravity here. Those two forces are happening because it's sitting on a surface. So while those are real forces, those forces are not what's going to go into our equation here, because those forces have nothing to do with this distance that's being covered by the book. That force that is causing that motion is this one right here. It's the force that we're applying. So this one is the one that we're going to stick in here for our force. The variables in this equation, they're the same. The force and the distance are the same as what we've used before. So notice that force and distance are the same as they've always been. Force is measured in newtons, distance in meters. But now we have a new variable, work. Work will be measured in joules. Joules is symbolized as capital J. Work is in joules. So I want to go through these, and I just want to ask you to think about, is work done in each case? If I apply a force to a wall and I become exhausted, I am not doing any work because that wall will not move. No distance, no work. If a book falls off a table and free falls to the ground, there is work done by gravity. Work is done by gravity in this point, which may be counterintuitive to you that gravity can do work. It's a force and it moves the book through a distance, so there is work done. A rocket accelerating through space, the rocket's applying a force and it's going a distance, so there is work done and the rocket moves. Here are some other scenarios. Think about them real quick, read them, pause the video. Alright, here are the answers to what you want to know for 4, 5, 6, and 7. Look at those real quick, pause the video, and make sure you understand why it is in each case. I will talk about number 4 right here. That's an important one to note, that there is no work done right here, even though we do have motion. When you carry a tray above your head, you are applying force to the tray, but the force on the tray is going upward on the tray, but your direction of motion is sideways. So since those two forces are perpendicular, this force has nothing to do with this motion. It definitely still takes a force to keep the tray from dropping, but that force doesn't cause the motion. So there's no work that's done by this particular force. There is work done in the problem by your legs. Your legs are what's causing the motion. but you're self-supporting the tray, there's no work done. Read this one, pause the video, think about it, and see what you think. A force of 100 newtons was exerted on an object and no work was done. In order for that to happen, the object has to have remained motionless. And the reason for that is, if work is force times distance, we do have a force. Work is 0. The only way for that to happen is if distance is 0. Look at this problem real quick and see if you can work it out. How much work is performed when a 50 kilogram crate is pushed 15 meters with a force of 20 newtons? Pause the video, work that out real quick, and see if you can get the answer. If you do it, work equals force times distance. You apply a 20 newton force. The box moves 15 meters. 20 times 15 is 300. Notice that we do not need the mass for this one, because this mass doesn't have anything to do with how far the box moves. The mass is creating a force that goes downward. That's the force of gravity, but that force has nothing to do with this force, which causes the motion. Alright, so the answer is 300 joules. Let's talk about power now. Power is simply the rate at which work is done. Okay, so power takes work, which is this W, and adds a time component to it. Power is work divided by time. So I don't want you to get this W confused with this W. Okay, this one particularly right here stands for watts, and watts is what power is measured in. Those are the units for power. As opposed to the W in the equation itself, that stands for work, and the units for work are joules. J. I'm sorry for my writing. So power is work divided by time. Power is going to be measured in watts or kilowatts. 1 kilowatt is simply 1,000 watts. Sometimes it's measured in horsepower, but I'm really not concerned about you knowing this particular conversion right now. Power is work divided by time. Sometimes you might need this particular formula as well. We can transform this. We know that work equals force times distance, so we can substitute that in, and force times distance, our equation becomes force times distance divided by time. And I hope you can remember from a long time ago that distance divided by time equals speed. So we can change it to force times speed. So we may have some problems later where power will actually equal force times speed. That formula is the same as this one mathematically. Alright, pause the video real quick and do this problem. If a machine performs 500 joules of work over a period of 100 seconds, how much power does the machine have? Well, all we have to do is take the work, which they actually gave us, 500 joules, divide it by the time. 500 divided by 100 seconds is 5 watts of power. Notice that time always has to be in seconds, which it is in this particular problem. Here's a tougher one. Pause the video and see what you get here. So we have an electric motor that's lifting an elevator, and the elevator goes 9 meters. It takes 15 seconds for that to happen, and the elevator exerts an upward force of 1.2 times 10 to the 4th newtons. So we want to know the power that happens. So in order to get that, we know that power is work divided by time, but this problem doesn't give us work, so we have to transfer that to force times distance divided by time. And they gave us a force, they gave us a distance, and they also gave us a time. So all we have to do is simply put all those things into this equation. Since they all are going parallel, our force is going up, the distance goes up, so we can put all those things in here, and it took 15 seconds to do that. If you calculate that out, you will get 7,200 watts. Now, we also want to know the answer in kilowatts right here. 7,200 watts. To change watts to kilowatts, all you have to do is move the decimal 3 places to the right, 1, 2, 3, or you can do unit analysis, and you would get 7.2 kilowatts.